So some of the guiding questions for how we sort of do our research comes from this sort of idea of backwards course design that people talk about in education, this idea of thinking about what should students be learning, how are you going to know if or what they're learning, and then what instructional approaches are going to improve student learning. And so from a physics education research perspective, you can sort of put a bunch of science research questions on there. In particular, what should students be learning is really a question of what is it that I'm trying to measure. How am I going to know if they're learning is how am I measuring it. And then what instructional approaches improve learning is sort of what variables am I going to be changing in testing. And so these questions are going to come up a number of times as we get going. But my research focuses on physics lab courses. So the first thing we need to talk about is what are the goals of physics lab courses? Why do we have labs in an undergraduate physics curriculum? So we're going to do this as a sort of think, pair, share. I want you to think for a moment to yourself, what do you think the goals of lab courses are? And you can focus on the intro level if you'd like. And then turn to your neighbor and have a quick conversation, and then we'll kind of come back together. Towards science, developing practical skills or problem-solving abilities, scientific habits of mind, or just an understanding of the nature of science and measurement. So you can hold up your fingers for 1, 2, 3, 4, or 5. Which of those things was sort of the biggest part of your conversation? On 3. Amazing. So in this room, I am seeing a lack of consensus. Which is representative actually in the literature. If you go through and dig into what do people think the point of lab courses are, there is no consensus on what the goals are. And sometimes the goal is to do all of those things, which you can imagine would be a pretty intense lab course. And on the one hand, that's sort of a problem in itself, but the more frustrating problem, as was mentioned in my introduction, there hasn't been a ton of research on published research on the effectiveness of different lab curricula. So we have a whole bunch of people who can't agree on what labs are for and no evidence to sort of back up any side. Good. Conditions, we found universities, departments where the lab course was optional, so you can compare the students who take the course, the students who don't take the course. And so an assessment, if our goal is to improve student understanding of course material, then the final exam should be a pretty good measure of whether they've done that. And a thing to note is that there are going to be some questions where there was a lab that reinforced them, and some topics that don't have an associated lab. So going back to our guiding questions, right, what is it we're trying to measure? Student learning of the content. How are we measuring it for the final exam? And then the variables that we're changing, taking the lab versus not taking the lab. Now, if you're a critical physicist and you are thinking critically right now, you should be freaking out about this one. Students who opt to take an optional lab are not going to be the same as the students who don't take this lab. So we've got to deal with this sort of selection bias. The way that we did that was taking advantage of this fact that not all concepts in the course had an associated lab activity. So you can take on the exam a ratio of student scores on the lab reinforced questions over their non-lab reinforced questions. And so all of the content is covered somewhere in lecture, tutorials, and discussion sections, and some of it is further reinforced in the lab. So basically what we're testing is that this ratio should be higher for the students who take the lab than for the students who don't take the lab. This is sort of the hypothesis or prediction that we're testing. Okay. So we've done this now at 3 different institutions, ranging from a small private liberal arts research-based institution in California, you can guess what that one is, larger public school, and then sort of a medium-sized institution. What happened here? Oh, okay. The slide is broken. But some of the similarities, or some of the differences here, we've got 3 very different institutions, different populations of students. We had a mixture of E&M and mechanics courses, calculus-based and algebra-based, a lot of differences, but some key similarities, which were all of these courses used all these institutions used their labs to reinforce the content of the course, and they were really designed to achieve that aim. So they would have things like, use the theory, the equation to make a prediction, does your observation match the prediction, explain what's happening, all of that kind of stuff. Oh, there. That's what I just said. Okay, so what I'm going to show you is we've got the 3 different institutions here, the courses at each of the institutions along the bottom, and then this ratio is going to be up the y-axis. And then I'll show you the lab students are going to be students who took the lab in the yellow, and then the students who don't take the lab in the gray. So we can do a sort of prediction. What do you think is going to happen? And again, we'll do a 1, 2, 3, 4, 5. The lab students are going to outperform the non-lab students. The yellow dots will sit above the gray ones. The students who don't take the lab will do better. The lab will actually hurt, so the gray students are going to sit above the yellow. Or there's going to be some weird pattern we're going to have to make sense of. There'll be no difference, or you have 5 fingers, so other. Give me 1, 2, 3, 4. Go ahead. I've got 1s, 3s, 4s. I'm seeing a lot of 3s. Weird and some 4s. Cool. Did anyone say 2? Did anyone say the last one? Okay, so ready? See what happens? Surprising? Not surprising? So within error bars, statistically across all of these different courses, there's no measurable difference between students taking the lab versus not taking the lab. So what does this mean? We call it labs are not providing a measurable added value to learning the course content. The idea that they are already seeing this material and the labs really aren't adding a whole lot beyond what they're getting. That's not to say that labs can't or aren't teaching them anything. It's not measurable. And given the resources that go into labs, that's kind of problematic. The other thing that's come out, so I think Heather Lewandowski was here last semester or last year or something, so you may have already seen this, but there's an assessment called the Colorado Learning Attitudes About Science Survey for Experimental Physics, the E-class, and it asks students a number of questions and then asks whether they, or gives them a number of statements and asks, do you agree or disagree with these statements? So for example, when doing an experiment, I try to understand how the experimental setup works. They should agree with that statement. And then when doing a physics experiment, I don't think much about sort of the systematic error. You would want to disagree with that statement. So you can look at what do students say at the beginning of ones that were designed to teach them experimentation skills versus ones that were trying to do both. Maybe surprisingly, maybe unsurprisingly, this is what they get. The labs that aim to reinforce concepts, even if they are also trying to do skills, lead to these huge negative shifts. Students become less expert-like when they're thinking about experimental physics by the end. And there's sort of this small positive shift if you're trying to teach skills of an experimentalist, which is optimistic, but it's pretty small, which is worrying. So not only are we not teaching them the content that we're trying to teach, but we're also decreasing their attitudes towards physics, which also leads to the picture that was on my poster, this one, which is a whole other level of frustration, that students will say that they want to be theorists because they hate their intro labs, which is just depressing on so many levels. So what do we do about it? Well, if we go back to this question about what is it that students should be learning, we talked about at the very beginning of this all of this other stuff that we could be doing with our labs, of course. We could be developing students' interest and motivation towards experimental physics, which is clearly something we've worked on. Developing their practical skills, habits of mind, and this sort of understanding of experimentation. So it's, clearly the labs, there's an opportunity here to do a lot of this. The other, just a quick note, the American Association of Physics Teachers in 2014 put out this list of recommendations for lab goals, and I think a lot of the ideas that I'll talk about that are sort of in this vein fall into these sorts of categories. So there's a lot of good recommendations if you're looking for some resources on what to do. But we'll go back to data. So, we'll say that. So the way that we've been thinking about all of these is through this lens of critical thinking, that in order to do an experiment and to understand experimental physics, I need students' brains on, and I need them thinking critically about data and evidence and all kinds of things. So my definition of critical thinking is the process through which you make decisions and decide what to believe, especially related to believing evidence and data and models and things like that. And we're going to go through an example of what this might look like in an intro lab, and then we'll sort of break down what happened. So we're going to start with the period of pendulum experiment. So in our intro physics lab, we have students measure, we ask them the question, does the period of a pendulum differ when released from different angles of amplitude, 10 or 20 degrees? And so the equation that they've seen in class, right, has this, the only dependence is on the length of the pendulum, so the angle shouldn't matter. This is about as much instruction we give them, so there's no buttons to press, there's no things. It's, they have to decide how many data points they want to take, how many times they're going to let it swing. There's a couple of decisions that are open and available to the students to play with. So we're going to do a case study. So one of the groups decided they would just measure the time for a single period. So they, it gets to one end, they press start, it goes through one period, they press stop, record that time, and then they repeated it 10 times, found an average, and then a standard error, standard deviation, and standard error. And then they did that again for the second angle. So the data they got when they did this was 1.84 plus or minus 0.08, and then 1.81 plus or minus 0.08, which is a difference of about 0.2 units of uncertainty. Okay? What does that mean? What does 0.2 units of uncertainty mean? It could mean the periods agree, the periods don't agree, the uncertainty is too large, the uncertainty is too small, or something else. What do you think? On three. 1, 2, 3. I have a lot of indecision. I've got 1s and 3s mostly. Okay. So this idea, they probably agree, but the uncertainty could be too big. Great. So we sort of operationalize this in something we call T prime, which is like a T value, but a little bit different. So you're taking the difference between the two means divided by its uncertainty, right? So this is what 0.2 sigma means. And so if we think 0.2 is small, then a small difference can either mean the values are close, like my numerator is small, or the uncertainty is too large, my denominator is too big, is how you can get a small number. And so you can immediately see that you can artificially sort of get agreement if you take a messy data set. If your uncertainty is big, you can artificially get agreement between two measurements. So what does that mean? So what should they do next? Once you have this information, what would you do? So just as a reminder, they measured single periods, repeated 10 trials, and then calculated from there. So
Because they're just measuring the period of a pendulum.
Because they're measuring the period.
It's not really exciting.
It's not very exciting. They want to get out of there as soon as possible. They would have left earlier if they could have. Okay. Well.
They've already been told the right answer.
Pardon?
They've already been told the right answer. They don't know why they're bothered.
They've already been told the right answer. They don't even know why they're doing it. And what did their data do?
They've already been told the wrong answer.
Sorry? What was that?
They've already been told the wrong answer.
They've already been told the wrong answer. Fair enough. We'll get there. Did their data agree with the equation or disagree? Basically agrees, right? So the equation says there shouldn't be dependence. They didn't get a dependence. Wonderful. Let's go home. Why are we still here? Cool. Now, what could they do next? As inherently curious and interested, critical thinking physicists, what would you want to do next? What possible things could they do next? Give me your fingers again. 1, 2, 3, 4, 5. Okay. There's a lot of emphasis on 2s, but I've got some 4s. I've still got some more 5s. And some 3s. So one of the cool things here, right? Any of these activities would be a reasonable thing to do next, right? There's no wrong answer here. Any of these would be fruitful moving forward. And there's lots of other types of things too. The group that we've been studying decided to measure more swings per trial. So we went through this crazy Socratic dialogue about what is your main source of uncertainty, starting and stopping the stopwatch. Okay, well, anyway, we went through that. They figured out that they could increase the swings. So eventually they get to doing 20 swings per start and stop of the stopwatch, which brings their uncertainty down by a factor of 20, and now we've got this difference out at 3.76. They've got this huge difference statistically between these two periods of pendulum. So now I'll show you the conclusions that one of these students wrote in their lab books. So the student says, the opposite of the expected happened. T improved is greater than 3. The measured values are different. Conclusion. The period of a pendulum does depend on the angle with the vertical in the initial position. The algebraically derived formula for the period is approximately 2 pi root L over G of the pendulum, which is only valid for small angles. Considering the results of this experiment, 20 degrees is obviously not small enough. Since the angle has an effect on the period T, it should be somehow represented in the formula. If you can make a precise enough measurement, you can show that the theoretical derivation of the equation of motion for a pendulum is just a good approximation, and reality is slightly more. All me, no. And the beautiful piece of this, right, is that last paragraph where it's, uncertainty is a physical thing now. It is telling me by reducing my uncertainty, I can learn new physics, right? I can see these approximations after come to life. It's just beautiful. And just full disclosure here, this is not a typical example. This is a typical example. We will talk about how typical it is later. So then the next week, right, of course, just measuring 2 degrees doesn't actually tell you that the angle dependence is what's going on. There's tons of things that could be going on. So the follow-up investigation, we have them measure it as a function of angle, and sure enough, you can actually figure out with a stopwatch that there is this sort of second-order quadratic behavior going on. Okay, so what just happened? So I said that this is an example of critical thinking. So this is my definition of critical thinking. So I want you to think this idea of, what is evidence of critical thinking in this process? How did they decide what to believe in this instance? sort of iteration, there's some sort of reflection that happens. It's not just doing the experiment once and leaving. And so one of the biggest things that we have to do, because the instinct is once you've proven the theory, I can just go home, is you literally, as an instructor, have to force them to do something here. And in our case, we usually start the semester with your goal is to try to, at every point, try to reduce your uncertainty, improve the quality of your measurement. That's what your iteration is sort of focused on, so that they can start to see that they can see physics. And then we push them later on into the, extending experiments and things like that. Yeah?
Did they really go point to the pendulums? That difference was so small. How sure were they systematic here?
That the pendulum had changed
Yeah.
length?
For step one, I mean, you tell me that small difference could be inverse, like a different length, right?
It's one, they're using the same equipment just over and over and over again. So there's, maybe it could have stretched. And so, if a student had said that, then I would, let's measure it. How big, you can even predict from the equation, how big of a length would it have had to have changed to get the effect that you just saw? Like, I could do an entire undergraduate program just doing periods of pendulum, I'm pretty sure. But eventually you gotta move on because periods of pendulum are boring. That's so one of the other things that of course we have to think about is, okay, we've observed this, but there's a really big question about, well, why is this actually happening? Why does this help students become critical thinkers? So there's a couple of things that we sort of borrow from psychology. The idea of comparison really just help you make sense of what's going on. Giving students some agency and freedom to make their own decisions, but also to make mistakes seems to be important. But feedback and support to learn from those decisions, as well as opportunities and time to actually revise and improve. And especially the thing that we really love are these situations where the physics isn't perfect, where we're actually going beyond what's in the textbook, we're finding surprising results, discovering new ideas, and they have to sort of deal with these disagreements, which is really fun. Okay, so I said that the example that we showed was a beautiful example, not a typical one. So we've got to talk about, well, what about when you have 900 students enrolled in your physics sequence? So we did this with two groups of students at the University of British Columbia. So we had 150-ish students in each group. We also have a control group and then who were sort of business as usual, and then this new group. Both groups had weekly 3-hour labs over 2 different semesters, same set of mechanics and dynamic experiments. They would write in their lab notes. There were no formal lab reports, but they would write in a lab book. And the experimental group got these instructions that asked them to iterate and improve on their experiments, and it was sort of faded out over the course. So by the end of the 2 semesters, the instructions given to the control group and the experimental group were actually identical, but they'd gone through this history of very different techniques. So one of the things that we can look at, right, is if we're asking them to iterate and find ways to improve the measurement, you can just see, did they do that? So you go through their lab books and just cross off sort of instances where they either propose a way to improve it, or the blue is going to be that they also actually changed it. So then the fraction of students will be up the y-axis here. And I've got a couple different things to show you. The pendulum happened in week 2. Then we jumped to the end of the second semester, week 16 and 17, where now the instructions are identical between the 2 groups. And then we have actually followed a number of students who took the second year electronics lab course. We looked at what they were doing in one of those labs as well. And so then we'll have the control and the experiment groups sort of side by side each week. So just a quick check. What do you expect for a control group who've never been told to iterate and improve their experiments? What fraction of them do you think will either propose or actually carry out a change or an improvement to their experiment? Less than 25%, between 25 and 50, between 50 and 75, or more than 75% of the students. I didn't even finish that, everyone's holding up. With some optimistic twos. Ready?
Yeah.
So the instinct to go home is real, right? Like they don't do this. Okay. But when in the pendulum experiment, this was high scaffolding, so we told them to iterate and improve, and sure enough they do. With a couple students at the top, they're not getting a memo, but that's fine. Now we jump to the end of the second semester, where everyone's getting the same instructions, and we've still got these huge gains it drops off a little bit, which makes sense, but obviously it's still a huge gain over this group. And then into the second semester, it continues. And these are in the second year, this is formal lab reports. They're telling us about the ways that they iterated and improved in their formal lab report. The other thing that we looked at was in these situations where the physics doesn't work, how do they deal with that? So we looked for instances where students even just identify, acknowledge that their results don't make sense or they have some sort of weird disagreement. And then the blue is some situation where they interpreted it. So the pendulum, right, they attributed it to the small angle approximation. We didn't grade for correctness. We were just scoring for, do you even try to make sense of this in some way? So now in the intervention group, right, we saw this beautiful example from the pendulum. What fraction of students do you expect would have come up with something as beautiful as that? Less than 25%. And this is the intervention group that we work with. Less than 25, between 25 and 50, between 50 and 75, or more than 75. 1, 2, 3. Sorry?
It's the intervention.
This is the intervention group, yeah, who we told to sort of iterate and improve on their experiment. I got the whole spectrum, 1s, 2s, 3s, and 4s. Okay. That's it, right? So that beautiful group is that group. This isn't a thing, this wasn't part of the instruction. The instruction focused on iterating to improve the measurement. It wasn't focused on evaluating models and deciding that the equation in the textbook was wrong. But over time, they learned to pick this up. And that continued again into the second year lab. And so, we're starting to investigate what this might mean. One theory I have is that they sort of shift their sense of authority from the textbook to themselves as experimentalists is one of the things I'm hoping is happening. It could just be that they've learned the rules of the game, that this is what happens in this class. But it doesn't, the fact that it continued into the second year lab, or we weren't involved in it at all, sort of says it's more than that, but that's still sort of an open question at this point. I'm gonna skip that. Oh yeah, no, I'm gonna go here. What time are we closing? 5 o'clock-ish, okay. So well, yeah, let's do this slide first. So I think it's sort of abstracting to the practical application of this. If you were to revamp your intro physics labs here, what are some things you could do? The big shift seems to be this shift from, my goals are on the process of the experiment rather than the product. So it's not, I don't care if they actually measure that the two periods are different. What's really important is how they get there and what their argumentation is and that sort of thing. But you need time to do that, of course, so we've been spreading our labs over multiple sessions. So rather than a new lab every week, they spend 2 weeks on periods of pendulum, much to their enjoyment, frustration. And then another 2 weeks on the next thing, that sort of thing. And then this idea of giving students agency, handing over some control to the students to make their own decisions and try stuff out. Removing some of the structure so the students are playing, but it's still constrained, right? So in the pendulum, they get to choose how many data points they want to collect, how they want to collect them. Some of the improvements, right, that students come up with when we say improve your measurement, they'll say things like they'll create these barricades to try to reduce the air resistance or air currents in the room. They'll put lines on the floor to really mark when the pendulum passes it. And then my favorite one is like, don't let so-and-so time because he keeps messing up. It's all good. Whatever goes, sure. Let me know how that works for you. And then the other piece is this, giving students using experiments where students really don't know the answer, right? So in this room, everyone's length of their pendulum was different. So there's no right answer in this room. The only way to know the period is by measuring it. So there's no experiment where they're measuring G or any known constants because we want to really force them on how are you going to measure it, what are you doing here. One of the things that we're playing with, I've got a colleague who's using this, sort of trying to do this in a upper division optics lab. And so for him, there's safety issues, in some cases there's time issues. So one of the things that we're playing with is in week 1, using sort of the old structured labs that they've always used, but then the second week is design and carry out some sort of improvement just with the equipment that you have, some sort of extension that is just a little bit outside of that. And so we're still sort of, unfortunately, we only teach about 10 students at a time, so not sure how much data we'll get, but we'll try to dig into that a little bit. Okay, so now when it comes to measuring, so one of these questions is how do we actually know things? what do you think the group should do next? Obviously, this is the normal we do. Currently, takes students about 30 minutes to answer it. We have a closed response version, so it's like they check boxes. It's all online, and at this point, it automatically generates reports that compare your data, your class to other classes. And we've been collecting over 1,000 unique student responses, which is crazy, and going through some validity things now. But just to give you an idea, so the two groups, in the one case, they measure sort of 10 repeated trials for 2 different masses, and then find the spring constant value, which came from when I asked students what does it mean to evaluate a model, they would always say it's about finding the parameter, which was surprising to me. The other group, on the other hand, measures 2 repeated trials, 10 masses, really a switch, and then they create this like linearized plot, residuals. They eventually actually find that it needs an intercept that isn't predicted by the model, and then you've got to make something with that, which obviously sounds familiar. Losing all my slides. And so some of the questions that we're playing with here, getting into what is it that students are, how are they answering these things? So one of the most recent results that we came up with, what should the students do next questions, a lot of courses the students end up shifting towards they want to reduce uncertainty, seems to be the thing that they latch onto rather than extending the experiment. So we're starting to understand what that might mean, but lots of fun stuff happening there. Okay, so the last thing that I'll do is just a fun little tidbit that we've been coming up with. So this idea of, I think I mentioned this idea about authority, and these students coming up with this small angle approximation at the end, but starting from this idea of the expected result that theory predicts that they should be the same. One of the things we've been looking at is how does having this actual expectation about what's happening influence what they do in the lab. You can sort of see where this is going. So one of the students at the end of this course I interviewed told me the pendulum experiment we did at the beginning of the year, I think that really made a mark on me because I went in there expecting it to vary 10 to 20 degrees to be the same because that's what I was taught. And then when you finally figure out that, oh, it's supposed to be different, then I was like, oh, I probably shouldn't be doing experiments with bias thrown in. So this is one of the things that we're starting to probe, this idea of do students actually show sort of a confirmation bias when they're in the lab. So my postdoc and one of my graduate students have been looking into this, and they found these statements in students' lab books where they would say things like, we didn't take out the outlier because it didn't match the average value we wanted to get. We decided to redo the outlier trial because there was a procedural error. The data we wanted to get? Okay. The other one, they get this T prime, so that's the difference in units of uncertainty of 1.7. We'll attempt to reduce this number through additional measurements, right? We are trying to get agreement between these. We chose to go back to individual oscillations because we liked the So we had actually gotten my graduate student to replicate the UBC analysis for the Cornell data, and then he came across these statements and was like, wait, what? So obviously one of our questions is, okay, well, how prevalent are these behaviors in the class, and what happens over time? Does this experiment actually really teach them that they shouldn't have bias going into the thing? The other thing that Emily's digging into is how does what they write, and this was written in their lab notes they submit to be graded. And so the question of what are they actually doing that's written compared to what is actually happening in the conversations. We've been videotaping students doing the pendulum experiments and seeing what they're actually doing and talking about. Do they know that this is not a good idea, or what is happening? Yeah, anyway, so that's questions. Lots of fun stuff coming up. So I think this is sort of the summary of what I've talked about, and that should give us some time for questions. So again, courses that we did, the labs were still correlated with the lecture, just not all students had to take them.
So we used to have a philosophy here that the first year lab would not be correlated with
Right.
course content because largely it was not about content but more about a lot of techniques and so on. But we moved away from that model to some large extent. And it's not clear that it would actually, because we actually thought that there would in fact be the lab would assist, but it was the other way around. In fact, it would make progress in the lab.
Oh, if they knew the content from
But
lecture.
yes.
Yeah.
So, but that been really assessed.
No, certainly not, unfortunately. But there's a couple of things. I mean, on the one hand, so it hasn't been tested, but I should say that, we're doing periods of a pendulum, we do Holmes law. The physics that we assume the students that we build from in the labs is all stuff that they should be familiar from, basically from high school, right? So we are sort of operating under that assumption of we're almost bringing the level of the physics content down so that we can do the higher level stuff. So in that sense, I would say, yes, that it certainly would be helpful if they already have the content knowledge to then do the experiments, except for this confirmation bias thing. And that's one of the pieces when we're trying to get students into this mode of model breaking. If they feel too strongly towards the theory, is that going to hurt them? But maybe that's a lesson that they have to learn. Who knows? Yeah, who knows?
So you talked about moving away from content, the lab. Do we just give up on content, or is there a way that we can teach content better in labs?
I'm sure there is. But there's two pieces to that. One is sort of bang for your buck.
Sure.
Given the resources that go into labs. So, and I skipped the slide where interactive lecture demonstrations have been consistently shown to provide really huge learning gains in a 15-minute demo where you have students make a prediction, see the demo, explain what's going on to each other. When you make it into this interactive thing, a 15-minute demo can create a measurable learning gain, which labs are not. So in terms of the bang for your buck, there are alternatives. The second part of that answer is if we're using the labs to teach content, where are they going to learn about data analysis and the nature of measurement and critical thinking and all of those other skills? It's sort of there's more to physics than theory.
So I have a question just on the last point. I thought when you were talking, I thought it was neat that the students came up with, it's the small angle approximation. Because even when not focusing on content, the content still seems to be reinforced.
Yeah.
So I've been a TA in the second year lab, which means a lot of direct supervision. And I've had this in my mind of trying to focus on the skills and critical thinking about what they're doing. And I find there's a lot of resistance from the students. So I'm wondering how you actually overcome that resistance.
Yeah. That's a good question. And we see that in the first year course as well, right? That especially when there's this philosophy that the whole point, so there's a study out of Rochester Institute of Technology where they surveyed students about what is, and the question I asked you, what is the point of labs? And even why do we have experiment? And the first thing that comes up is experiment is to verify theory. It's to prove that the equations in the theory are true, as opposed to experiment for the sake of discovery and those sorts of things. So I think that until you can get them into this mode of there's more, experiments do more than just verify truth, they also discover new truths. I think that's a big part of it. So this sort of shift on, it's not about shifting the assessment and the goal isn't on what you get in the end, it's just about how you get there and figuring out how to actually assess that, of course, is the big question. But it requires that sort of mind shift towards the process rather than the product. That's like, but it's hard.
You said that you should try to get the students to think more about discovering new information rather than confirming it. But then how does that go well with just swinging a pendulum, which is, in their minds, there already exists a theory for that. We've known it for 400 years or so. So have there been attempts, have there been attempts in making labs that try to do things that students can't just look up on Wikipedia in 5 seconds, like look up the answer, you know?
So in biology, there's this move towards course-based undergraduate research experiences, cures they call them, which the idea being, let's give them situations where they're actually doing sort of cutting-edge physics, well, in their case, biology research in a course-based setting. I'm not sure about scalability of that side, and in physics compared to biology, we face the issue that the history of what we know in physics is so large that getting them to the point of cutting-edge physics, of course, is tough. So what that actually looks like is difficult. The piece that we, when it's, I think, I hope, and this is a testable research question, if you can shift the focus on, we are not here to learn the physics, we are here to learn the process, then you can very quickly say, I don't want you to Wikipedia things, just don't do it. You can Wikipedia this as much as you want when you get out of this room, but while you are here, the only way that we are going to know things is through the experiments and empirically. And so using things where they don't know the answer, right? So this idea, they've seen the small angle approximation in class, but for some reason it just doesn't come to mind in this space. And so using situations where they don't know it immediately allows them to figure stuff out. So it's, but it's an open, testable research.
I think there are lots of first-year physics experiments where we don't know the answer that we can design and do. One that I saw, a brilliant experiment, was simply to take a thumbtack, an ordinary thumbtack, and throw it on the table and measure the number of times it ends up lying on its back versus the times the point is touching the table. And then you give them a whole box of thumbtacks. You have to think about that question. That's the probability that the thumbtack will land this way or that. And you can't calculate this, but you can do it with a box of thumbtacks.
And there's tons of experiments where,
I was going to ask, it seems to me that a lot of what you're talking about is physics culture. And the students, so most of them, the tough students that we teach are biology-oriented students. And so there must be some kind of whiplash that they go through. When they come to the physics lab, they're supposed to think one way, and they go to the biology lab and they have quite a different hypothesis testing kind of paradigm.
Yeah.
So, do you ever try to address, do you ever explicitly say, this is how we do it in physics, as opposed to how you may have learned it in other?
Yeah, there are a couple of places where that does come up. So, for example, the word trials actually means something different in physics and biology. So there are some very literal terminology types of things that we have to talk about. As much as possible, I think if you can abstract this to this is how science is done, we do that. But that being said, we do actually have an activity where we have students draw flowcharts for how we do experiments in physics. And we do very specifically put the physics word in there to sort of just hedge that off right away.
A couple of years ago, we had an exercise where we were supposed to formulate questions for the students to be asked during course evaluation. And a huge committee spent 2 years. Psychologists came up with hundreds of questions that we were supposed to choose from. And the only question about experiment science was, this course helped me formulate hypotheses. Yes or no? The university actually believed that a course should help you formulate hypotheses. That was the only scientific
possible way. And so, but the hypothesis testing is an interesting thing. And I think even the idea of starting with a research question is sort of not really how it happens. You know, a research question comes from reading a bunch of papers or reading a bunch of results or doing an experiment yourself. It always comes out of something. You don't just grab it out of thin air. So I think there's a lot of things like that need to sort of get reshuffled. And I think if you just turn the whole thing into a circle, that would make a big difference.
All right. Well, let's take a speaker.
always quick to take everything down.